let's look at the next topic we're looking at here, how about differentiability. Okay, so before getting into exactly what differentiability means, let me bring up a demonstration problem here. So how about let me call that just a demo problem here. In this demo problem, we are given how about the function f of x equals the absolute value of x. And you guys go ahead and spend some time writing it down. What we wanted to do with this function, we want to find the derivative of this function at 0. Okay. And yes, really speaking, it means we want to find the slope of the tangent line. Right? That's the meaning of derivative. See what I'm saying? Right? There will be many occasions where I keep reminding you that the derivative at a point, right, at a given value, is the slope of the tangent line at that specific value. So for this function given right here, this f prime of 0 means I want the slope of the tangent line. Right? After x equals 0. Right? So you're gonna have to constantly keep that the reminder when you read that about the meaning of the derivative. So let's find that. And so at this point, we've gone far enough into derivatives so that we've learned some of the derivative rules, right? The basic limit rules, and then there's the power rules that we've learned, right? So here's the thing. So naturally, at this point, when you've learned some rules, the first natural sense is that we're gonna try to avoid using the limits, right? Because we don't want to go with the limits; it's too long. See what I'm saying? No? So think about using the power rule. How do we find the f prime of x? Because using the power rule means that you're going to come up with some general f prime of x, right? From our absolute value of x function. You guys follow with me on that? But then the only rule we've learned so far is the rule to take the derivative of a power function, the rule for the coefficient, the rule for term by term, the rule for constants. This function here again fails out all of those, right? Someone may argue like this. Absolute value of x, right? Taking the derivative, we know it's the power 1 on the absolute value. Okay. And so making it, taking the derivative here, making it to 1 multiplied down an absolute value of 1 minus 1 right here. But let me tell you, it's not really true going that route. See what I'm saying? No. Okay. And absolute value is something that you got to move on extremely cautious. So now my point is that the power rule that we've learned and we love using it, the power rule, right, is just simply not applicable here. Really, we can't use the power rule. That simple, nice rule that we've learned, can't use it here. Okay? Because whatever the work here that we thought that was the way, it's not true. Okay? It's not really true with that. Okay? And of course, right now at this level, you guys are quite beginner into doing that. So it's hard for me to explain why this fails to work. But you're gonna need to wait to some more advanced course to get that better, solid understanding for that. But it points out the power rule is basically not applicable for this situation right here. That means that the plan about finding some general derivative is not going to work, right? So sadly, I have to take away that plan. So now that option to find a general derivative is out. We throw it away. So we got rollbacks. Anytime that finding a general derivative plan fails, we got to roll back to the limit definition right now. So here's the thing. I want the function, the problem wants us to find f prime at 0 specifically, right? The derivative of the function at 0. So that means we always have that starting point, f prime of 0, the slope of the tangent line at x equals 0 is given to be the difference quotient f of x, f of 0 plus h in this case, right? Minus f of 0. See what I'm doing there? We roll back to that very fundamental formula we've had long ago, a little while ago. Over h, check the limits as h goes to 0. I'm talking about we got to roll back all the way to that grounder, right? And we go from the ground up again. And then so in that way, right here, in this, according to the setup, right, applying this setup into our function right here, I'm looking at, see, the function here is the simple absolute value of x. And so that means here substituting 0 plus h into our function. We're looking at 0 plus h minus absolute value of 0. You guys agree? Okay. And we're dividing that by h. Check the limits. As h goes to 0. And right now I do assume that you guys are familiar with the graph of absolute value of x, but we'll talk about that even later. Okay? You're not required to be the master at this yet. But as far as the algebra that I substituted the 0 plus h into the function, you guys all check with me right there? Okay? All agree? Okay. So, needless to say, 0 plus h is just simply h, right? So in the next step, I'm just going to rewrite the expression. So the expression here in the next step is going to look as follows. Absolute value of h, right? That's what the first term here turns into. What's absolute value of 0? 0, right? Absolute value of 0 is 0. That's why the entire numerator here reduces down to just that. And then now over h. And then we take the limit as h go to 0. You guys agree? Okay? But this is where our danger comes out right here. So we got to really move on cautiously. Please do not just cancel the h's away and give me a 1. You see what I'm saying? No? It's completely out of charge with that, because there's a reason why we retain that absolute value sign. It's not simply just, absolute value of h over h. See what I'm saying now? So in that way, upon our realization that, hey, the absolute value sign is what brings so much trouble, right? What's bringing so much trouble? So we got to come up with a plan to get it out, to get the h expression outside of absolute value. See what I'm saying? And I've taught pre-calculus all over these years, and yes, students suffer really bad, and students, and including myself, hate absolute value symbols. So we always got to find a way to get it out of absolute values. So here, another reminder for everyone. You got to bring back algebra again, but when you have an absolute value of x, right? The truth is, in order to get that out of absolute value of x will equal x, simply just equal x, but only true for x greater than or equal to 0. You guys remember this from pre-calculus? It's simply the idea that the variable x itself, right, could be negative or could be positive, but the absolute value is purposely making it positive. See what I'm saying? That's why I think about absolute value of 3 right here. If the value 3 was already positive, right, then it's just simply equals 3. You see the connection right there? But then think about when you take absolute value of a minus 3, right? There's a negative. The value of the variable could be negative itself, right? The answer is still going to come out 3. See what I'm saying now? Okay, the answer is still going to come out 3, but the connection between the final absolute value and the beginning value right here is that we put a negative. Right? We put a negative sign to that original negative. The original value was negative, but to always enforce that the output being positive, we put a negative sign. Does that make sense with that? And so in that way right here, the absolute value function, on the other hand, see, when x is negative, like the case I just demonstrated here, then we have to write the final output as a minus x. There you are free from the absolute value symbol. Right? So that's the way how we get to our expression outside of the absolute value, the symbol. But now here's the dangerous part. When we apply that piece of understanding into our problem, so we have the absolute value of h right here, right? And then over h, and then h goes to 0. And now we want to get that out. So that means what? Just the h itself, when we apply that in our problem, just the h itself, it means h, absolute value of h of this little function right here equals to h if h is greater than or equal to 0, right? We strictly just apply that, and then it's going to equal minus h if h is less than 0. Okay. And so that means we have a broken up piecewise function right here. The function here is defined piecewise as 2 separate pieces. And so now taking this limit, when h goes to 0, has to be done as 2 separate limits right here, 2 separate sided limits. So from the left-hand side, right? For the left-hand side, I'm going to produce, hey, absolute value of h over h. But I'm taking the limit as h goes to 0 from the left-hand side. Remember that familiar, the limit operation right there? We're taking the limit for this overall function from the left-hand side. Now, if h comes to 0 from the left-hand side, means the value for h is negative, right? Are you guys with me on that? That means that having h being negative, I can rewrite the absolute value here as minus h on top of that. So my numerator becomes minus h. Now we are free from absolute value. Minus h over h. we take the limits as h go to 0 from the left-hand side. And then now with our absolute value, now we can easily divide. And so that gives me now, see, negative limits problem of -1 as h goes to 0 from the left-hand side. So we're taking limits on a constant function now, constant function -1. But from the left-hand side, so basic limit law tells me, the limit law tells me that this will come out to simply be -1. Okay, so from the left-hand side, we obtain a -1 limit right here for that problem. From the right-hand side, unfortunately, let's look at the situation. Yes, I'm going to roll back to that main function, absolute value of h over h. Take the limits to 0 from the right-hand side. Okay. Now, from the right-hand side, when h comes to 0 from the right-hand side means, see, it can come from 1, right, and then 0.5, and then 0.25, and then 125. Those are all positive value. Positive value. That means I'm going to rewrite absolute value of h as just simply h, right, and over the h in the denominator. See, so this time I took h out of absolute value and without worrying about putting a minus sign there. And then I'm taking the limit as h goes to 0 from the right-hand side. Right? So now h cancel with h, give me just a positive 1. Taking the limits when h goes to 0 from the right-hand side, it gives me what final limit is that? From the right-hand side. It's going to be a 1, right? Yes, the function remains constant 1 here. But now this is where the sad truth comes in here. Left-hand side limit came to -1, right? The right-hand side limit came to positive 1. And the problem did not ask us to do the two-sided limit. The problem asked us to find the general both sides limit, right? Because that's the way it is. So now what do you say about the overall, see, absolute value of h over h? The overall limits as h come to 0 generally from both sides. What do you say about this answer right here? It does not exist, right? The answer here is D and E. That's what I'm saying now. Okay? So this is the first problem that we ran into, that kind of problem where you remember finding the derivative at 0 or at whatever given point here means we're trying to find a tangent line. But now the limit result just turned out right here. You know what it means? We were trying to find a tangent line and we fire up the limit process, right? And then at the end it says the answer does not exist. So what does that mean in terms of the tangent line right here? There's no tangent line. No tangent line at x equals 0 for this function, absolute value of x. The function was absolute value of x. We were asked to find tangent line, the slope of the tangent line, right? But then that slope is a non-existing value right there. So I'm saying there's no tangent line. Allow me to bring up the graph. How's that? Okay.
Yeah. I'm not speaking something.
All right. You guys ready to see it? Here's a blank graphing space right there, right? This is the graph for absolute value. See that line right there? Okay. So no one's surprised about that one, right? Here's the reason why I'm saying that the graph has no tangent line right here at x equals 0. And by the way, x equals 0 is right here at that sharp point angle where my mouse cursor is pointing at, right? And so now think about a situation like this. Yes, you've been saying that you can place a line. You see, anywhere on the left-hand side of 0, you can place a tangent line. Imagine that this is my tangent line. This is my tangent line. It's short, but it's a tangent line, right? You can place a tangent line here, 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 anywhere on the left-hand side of 0. As a matter of fact, the entire line itself right here will coincide with the tangent line, but as long as you're on the left-hand side. Are you following with me on that? Okay? So, but then when you hit right at that corner, where do you really place a tangent line? Do you place a tangent line this way? Or do you, right at 0, do you place a tangent line that way? You see what I'm saying now? Or do you place a tangent line like this? Right at that sharp angle? Or do you place a tangent line kind of like this? We don't know. See what I'm saying now? The tangent line exists, but only anywhere to the sides of x equals 0. Right at the instant x equals 0, the tangent line just failed, doesn't exist. It's a sharp corner thing right there. See what I'm saying now? That's the reason why. And you see, if you place a tangent line right on that piece right here, what slope is this? -1, right? 1 fall, run, right? So was that consistent with the limit on the left-hand side that we saw on the board earlier being -1 right there? And then but switching to the right-hand side, what slope is this line right here?
Just one.
Yeah, just one, right? Is it consistent with the limit on the right-hand side? Indicating that, say, left-hand side and right-hand side, we all had the tangent line slope right there, but just right at 0, we won't. That's the idea right there. Okay? And so, that's now the first time we introduced that concept right there where we don't have a tangent line existing at that place. We fail finding a value for the slope. Precisely speaking, there's no tangent line existing at that. Right? See, left-hand side, we got a equal to -1, right? So what's that? Line falling down here. The right-hand side limit, the result came out +1. It was a line going up like this. Right? But then just right at 0, when you come close to 0, it just doesn't exist. So now we're starting to realize there are cases, there are instances out there where we cannot obtain tangent lines, right, at one single point on your graphic there. And that's where it comes in with this term about differentiability. Right? So let me write down the formal definition. So a function f of x, right, is said to be differentiable. At a given point x equals a here. So a function of f of x is said to be differentiable at x equals a if the derivative f prime of a is defined as the limits, right? So that's the definition for what it means by a function being differentiable. Exists as a finite value is quite important. So think about it on the other hand right here. Sort of like a special note here, right? I would say otherwise, meaning if that limit does not exist or anything else does not exist or without being a finite value, that's what I meant by otherwise. Otherwise, f of x, right, is not differentiable. Differentiable as given x equals a. So differentiable is now that term we just now defined this. It's more like a property. It's a property of your function at that singular point there, that particular point, value point. Okay. So whether it's differentiable at that point or it's not differentiable. All right, got a definition completely written down so far? So here's the thing. So with this definition, when we apply that to the demonstration problem we've done just earlier, the function f of x here was absolute value of x, right? Were we able to do this process right here? We apply that process at x equals 0, right? But were we able to obtain an existing limit? We were not able to, right? Indeed, we failed. We came to a does not exist. See what I'm saying now? So now, precisely speaking, this function, but only at x equals 0. So I'm saying this function is not differentiable. It fails that property, right? It fails that property right here at x equals 0. Anywhere else is fine, which is right at x equals 0. That function did not have a tangent line. And so I keep making that connection. So yes, you can also, from this point on, you can also make that connection like that. You see, differentiability, right? Meaning differentiable or not, right? So differentiability means having the tangent line. That's the value. Okay. Otherwise, it means we don't have any tangent line at all. Now let's get to an example here. Example 1. It's our new topic right here, so I'm starting the example number. So in this example, we go a little bit theory. We want to show that it's not differentiable at x equals 0. And each one of these functions that I'm showing throughout the examples, including that demonstration problem, has some graphical meaning as well. And we all going to put it together when we're all done. Okay, so we wanted to show that it's not differentiable. The definition is still there on the board, right? The value given here for the function is x equals 0. But differentiable at x equals 0 means this limit that once we set it up, has to finish all the way through and get an existing finite value. Otherwise, you set up that limit like that, right? And so in this problem right here, we're looking at at 0, so you're going to have f prime of 0, right? We set up the limits right here. If that fails right here, right, then we're going to say it's not differentiable at x equals 0. And that's the plan about how we apply this definition into our function. Okay, so we definitely have to roll back to the limit definition. We don't have a direct formula for this. I mean, we do, we use the power rule, but it's not as straightforward. So, just a start, f of 0, f prime of 0, right? The starting point here is we set up that famous difference quotient, 0 plus h, f of 0 plus h, minus f of 0. And we divide that by h, because we want to set up the formula to calculate slope of tangent line at x equals 0. That difference quotient is set up as a limit problem. And now, directly into the function, right? We're looking at cube roots of 0 plus h minus cube root of 0. You guys agree? Right. Divide that by h. And we take limit as h goes to 0. But so this expression now, after we apply the limit on the difference quotient into the function here, then it's simple enough to just rewrite it as cube root of h, right? Over h. Because cube root of 0 is always 0, right? And then we're taking limits as h goes to 0. All right, and then we can cancel, we can reduce this rational expression, this fraction a little more here. Limits h go to 0 over here. Cube root of h cancel into h here, giving me a 1 over h to the 2/3 power. Are you guys able to follow the algebra right there? Okay. Well, we're looking at the h, cube root of h means the h to the 1/3 power divided by h to the first power right there. Right? So dividing these right here, we're subtracting. Okay, that's the same as the h to the 1/3 times with h to the minus 1, right? Combining the powers right there, right? Combining the power is h to the negative 2/3. And that's the same way of how I'm writing this. Okay? And that's just one interpretation right there, one way of explaining it. All right. Let me bring down the graph here for you to understand the limits. So right now, focus your attention to the limit problem right here. We want the h get to 0, right? Generally from both sides. Before we decide to tear it down to two-sided limits right here. The function here is 1 over the variable to the 2/3 power, right? And let's see if when h goes to 0 right there, what's going to happen to the function. So, all right. So here's our function that I prepared. And you guys okay that I use the x variable right there? So we want x get close, right? We want x gets close to 0 from both sides, so here's the graph. That's the graph right there. Okay. So now see, this is the graph for 1 over x to the 2/3 power, right? So what happens to the function before we even have to decide to to tear it down to two-sided limits? As x gets close to 0 from both sides, right? They both what? Growing up. See what I'm saying now? They both growing up like that. Okay? And so in that way, now that we're seeing the graph here, then we can decide that, hey, this goes to what? A positive infinity. See what I'm saying now? So in my argument, the limit does exist, but it exists not as a finite value. See what I'm saying now? What we need is to exist as a finite value, like a 5, like a 10, like a 1,000, right? But here it exists. It shows the direction where it goes right there, but it's not a finite direction. I mean, it's not a finite value right there. See what I mean? So in this case right here, right? So in this case right here, you're looking at the conclusion here saying that f of x equals the cube root of x, right? Is not differentiable at x equals 0. See it now? And then because the screen is so slow right here. Let me get you guys into another problem, and then we're gonna look at the graphics all together. So right now it says it's the function, this function does not have, is not differentiable at x equals 0, right? It also means the function does not have a tangent line. See what I'm saying now? Okay, so let's call it example 2. Okay, we want to, once again, we want to show that the function is not differentiable. All right, so for this function, once again, showing differentiable or showing non-differentiable, it's all about we're starting with, well, that derivative we desire if we at x equals 0, right? Has to be set up as a limit formula here. So limit of f of 0 plus h, that's the given point again. So most of my examples, if you notice, I've been using 0 and 0, but it doesn't always have to be 0, right? So, but the point is you set up the difference quotient at that center point, that subtract f of 0, that difference quotient here we divide by h goes to 0. All right, and you can notice now, before I even get into the formula itself right here, just right here in this problem, think about 0 plus h is easy enough to understand, it's just h, right? So it's f of h minus f of 0. Now f of 0, when f of 0, when x equals 0 over here, which piece are we using? It's the piece right here, right? So f of 0 here, we're going to give a just, right, subtract the 4 over h. And then we take the limits as h go to 0. But I have to kind of write it in a hanging way right here, because we have to decide as h gets to 0, right, we have to decide which one is the correct piece, the proper piece that we're using for this function here. It's a piecewise function. So I got 4 because f of 0 is clearly according to the definition of our function. We use that piece, right? And so now here's how I'm seeing it. We have to tear it down to the two-sided limits. Left-hand side, right? So left-hand side gives me, when the limits follow it, h go to 0 from the left-hand side. F of h minus 4, right, over h. But then in this case right here, we know further that when h comes to 0 from the left-hand side, it's these values, right? So I'm going to have to substitute h into this piece right here. So I'm looking now at minus h minus 3, and then I'm subtracting 4. Right? And then putting that over h, I'll take the limit as h goes to 0 from the left-hand side. And then this is coming out easy enough that we can't, I mean, that's a minus 7. Okay, so we've got minus h, minus 7 over h here. Right? For h, get to 0 from the left-hand side. And so with those limits here, we're looking at, we can algebraically turn that into two separate terms. So minus h, cancel with h here, give me a -1, but then minus 7 over 8. So the expression came down to -1, subtract the fraction 7 over 8. And then we're letting h get close to 0 from the left-hand side. Now allow me to remind you, but so these two terms here, right? When you apply the basic limit, the limit laws of these two terms here, that first term stays as a constant, right? As we take the limits, h go to 0. But then the second term right here, think about the function -7 over x right here. Then with a function like that, right? When x gets close to 0 from the left-hand side, the function is indeed gonna rise like this. See what I'm saying then? Okay. So coming from 0 from the left-hand side, that's what it's doing like that. So that means it's going to positive infinity, but adding with a constant term right here, right? The overall limit here is going to grow to positive infinity for the left-hand side limit of our differentiating problem right here. So I gave the graphical arguments for that. And in case you're not convinced, in case you're worried about whether you have mastered the graph, think about it. I've mentioned earlier that we've had these kind of problems here when we have a coefficient, right, over x minus a pole right here, and then we raise that to a power n. Remember that form? Right? So this function, when we let x get close to that pole value a or this, right? Then it's going to go, once again, remember the result here is it's going to go dne for the n power is odd, right? For the n power being odd, like that. And it goes to either a positive infinity, right? For n is even, right? And and then a is the coefficient on top is positive, and then we go to negative infinity when n is even again, right? And a is negative. But then, see, the case that we have right here is -7 over the h or over the x. My explanation earlier, the way how I'm seeing this function here is indeed, see, the -7 is in place of the area. And it's really, it's h minus 0, right, to the first power, so it's odd power, right? And it's going to that pole right here. So now when you take the limit for h, you go to 0, right? But then here's the thing. The generality I introduced earlier was showing that it's a dne. Yes, if it's going from both sides, it will be a dne, right? But the reason it goes to the neat reason that it goes to dne because the two-sided limits are going in the opposite direction. And so now we can kind of from this problem right here, we can kind of come out with another sort of like a deeper level of generality that this pole right here. You guys can take a note of this. X over the coefficient over x minus a to the n power. We're letting x approaching the pole from the left-hand side. See what I'm saying now? That may go, once again, that can go to a positive infinity. Right? If a is negative, and then that goes to negative infinity. Right? If a positive value, just the left-hand side limit. See what I'm doing there? And that's generality here applied for our problem here. Our problem here, we're looking at limits for h go to that pole right here from the left-hand side, so that's why it went to. And then this number right here is a negative number. That's why the answer came out being a positive infinity. Okay. And then since I got into that way, from now on we can come up, we can keep this as a one general rule that the coefficient, okay, over a, I mean that coefficient a over the x minus a little a to the n power, and we're still talking about for n being odd, right? Specifically, right? For n being odd, specifically here. And this particular value, this particular setup, when x gets to the pole from the right-hand side, it will come to, okay, this will come to positive infinity. If a, now it's backward, if a is positive and then negative infinity, if a is negative. So write that down carefully. The two requirements for a here is kind of like a switch in the two cases right there. All right, and so now I'm going back to this problem right here, and that is the reason why we have this limit going to the positive infinity. Now, but what we've done up to this point is only the left-hand side of our current problem, right? So we have to also consider the right-hand side. So now I'm going to erase this work right here. And let's consider the right-hand side of the same limit problem. So the point right before that, right? That point right before that, when we came to this general setup right here, x coming to 0 generally from both sides here. Now let's tear it down to the right-hand side. So for the right-hand side, right, f of h, think about coming from the right-hand side of 0 over here. It means the h value have to be positive, right? So substituting a positive h value into the function, we must use that piece of function right there. You guys following? Because that's the indication right there when we use inputs greater than or equal to 0. So now I'm looking at h squared plus 4, right? And then I'm subtracting 4 here. So this is f of h for h greater than or equal to 0. Minus 4, and then we divide it by h, and the limit now is the limits. We're letting h get close to 0 from the right-hand side. Okay. And so now once you land it successfully into that step right here, then once again the algebra can just start coming out right here. So we will have h squared plus 4. We moved out with, taking out from the parentheses and minus 4, so the 4 here will eventually cancel. We still divide it by h, right? That difference divided by h. in the denominator, and we take the limit as h go to 0 on the right hand side. Okay? So now that in the next step it turns into h squared over h. Let's reduce this down to h squared over h as we're taking the limit h goes to 0 from the right hand side. So now the next step, we can see further that we can cancel the h here with that, right? That common factor h in both numerator and denominator here. So we're looking at just simply h reduced down to that, and then h coming close to 0 from the right hand side. So this time, what is the limit for this one right here? It's a 0, right? So now think about it as I just need to remind you that same setup right here, that same setup, right? You see the same setup, f of h minus 4 here, right? Divided by h. This is the difference quotient. But if we're letting h go to 0 from the left-hand side, we came to positive infinity, right? The one just now, f of h minus 4, right? We're dividing by h. We take the limit as h go to 0 from the right-hand side. This answer came out as 0, right? So do the two-sided limits agree? They just don't, right? And right from the first day that we've been agreeing with that together. So now that tells me that this limit, for this limit for h going to 0 generally from both sides is going to fail to exist, right? It's a DNE here. So that means the limit of f of h minus 4 over 8. As h goes to 0, on both sides, this is a non-existing limit. Does not exist. Okay. So now, as soon as we have just now pointed out that the limit here does not exist, means f prime at 0 does not exist, right? Or in other words, the function that we have defined here is not differentiable at x equals 0. In other words, we fail having a tangent line. You know what I'm saying? Okay. So now the ultimate conclusion here is f of x, right? It's not differentiable. It's not differentiable. And then you specifically at that value x equals 0. Right? That's how I'm showing it. So differentiability that you guys are learning currently doesn't have a direct assignment problem that goes along with that. I mean, back in the old days, they used to have a problem for you to learn to decide differentiability. But in these days, here we still teach you guys that, but you don't necessarily have to practice too much of that here. But it's good to understand that, so that when you go to the higher course, a lot of time you got to watch out for differentiability of a function. So we've been, there was that from the earlier lecture when I started getting into this, there was that demonstration problem, right? On the absolute value function, and then we've gone through a couple of examples up to this point right here. So in general, here's the graphical interpretation right here. So think about graphically speaking, right? The absolute value function I brought up right here sort of like represent a general case that we got absolute value, and then we got sharp angle. See what I'm saying now? Like that absolute value was a famous V shape where the corner right there was so sharp, right? And somebody in this class was, at first talking to me about we thought we could place a tangent line there, right? But in the end, how do we place a tangent line there? See, at that sharp corner. See what I'm saying? And so that demonstration example will show that the sharp corner, when you have your graph appearing to be a sharp corner at a value x equals a, that's where it's not differentiable right there, failing to have a tangent line, right? So, no tangent line. That's one criteria that you can detect graphically where it has the no tangent line, or in other words, the formal name for that is not, the function is not differentiable at that x value given the sharp corner. You guys all with me there? And sharp corner doesn't always have to be like a straight figure like this. It could be something like you jumping up as a curve, right? And all of a sudden, just turn it away. That's another sharp corner again. See what I'm saying? And then there are so many various situations about sharp corner. You can go like that, and then see what I'm saying? Sharp corner again. It may violate the function rule a little bit, but see. the idea is about the certain thing about we place a tangent line. Yes, we were able to place a tangent line on each side, but right at that point, how am I going to place it? Like this, or like that, or like what? We don't know. See what I mean? So those sharp corners is one case where the function fails to be differentiable, or the function is not differentiable. And then in another case, think about, I worked through in example 1 that we had right after the definition. The cube root represents a special case here that a lot of times you have a tangent line that indeed, the mathematical problem turn out to have an infinite tangent line, so it's not exactly a DNE, right? But we need the tangent line to be, the slope value to be a finite value, but the problem we have here really was what? It's a vertical tangent line. If you really attempt to place a tangent line for the x cube function, the x cube function looks like this. Cube root of x, not x cube, cube root of x. That's the one we brought up in the earlier example, right? And so think about if I attempt to make my best right here to draw over here, but if I really attempt to put a tangent line here, then the tangent line, it will be there, but it's going to have an infinite slope here. It's going to be a vertical tangent line. So cases like that, that's where also derivative fails again. The function fails having the slope of the tangent line. So vertical tangent, right? That's where we also fail having a derivative. The derivative equals the slope of the tangent line. So either we don't have a tangent line at all, or we have a tangent line, but that's a vertical tangent. So we won't be able to calculate the slope anyway. Okay. And then the one just demonstrated throughout the example we just finished here. That's the case of representing when you have discontinuity. Discontinuity. Your function that we use here in this problem was obviously something like this. And you know what? Let me bring it on the screen right here to show you guys quickly show you guys the function. Okay, so I'm going to bring up the graph here for us all to view that the graph of the example that just finished. All right, so here's the graph. Okay. You see how it's having a jump right there, right? A discontinuity. So that discontinuity is happening right at x equals 0 right there, right? We have a jump. So on one piece to the left is of x equals 0, it's some shape right here of the graph. And then when we switch over to the piece on the right hand side of x equals 0, then we have another piece right here, right? We've got two separately defined pieces. Right. And so in that way right here, that's why I think about it, if I had time to place a tangent. So if this was my tangent right here, right at that point, we even have a battle. Are we placing a tangent to be like near this guy, or are we placing the tangent down here? See what I'm saying? No, right at x equals 0, right at x, that the jump point right there for x. And that's the reason why. Okay, so now on this board here, this continuity is also another place where anytime you recognize this continuity or a jump into a function, right? That's where you have a non-differentiable function. So think go like this. There's a jump, right? And that, see what I mean? The function might have a break right there, right? At a value x equals a. Or, this continuity could have also happened like this, right? You got two pieces going to the same limits, but it leaves out that hole right there. See what I'm saying? And that's another example of this continuity. Okay? So these are all quick graphical cases that once you're looking at the graph, you can tell that the function fails being differentiable, right? Or is not differentiable at those points x equals a. Okay? And so just now I brought into the picture over here, there's some connection between being continuous, right, or having a jump discontinuous here and something related to differentiability. So indeed we do have a theorem relating that. So let me bring in the theorem over here. Now, so the theorem starting out, if we know that the function f of x is differentiable, so if we know that f of x has a tangent line with the finite slope, right? At the given value x equals a, right? If we know that information, then we can imply that, right, the function f of x is continuous. So we can kind of imply, think further that the function is continuous at x equals a. So this theorem right here is just straight out from the wording of it. All we can say is, hey, if we know the function is being differentiable, then we will know that the function has to be continuous at that point. But see, knowing this information is not too important. But then, now let me show you guys a little bit of a logic right here, and then later on, sometime, who knows, some of you will run into a formal course in logic, and that's where you learn these things more formally. But the way how the statement here is indicating, see, there's an if and then statement, right? So logically speaking, a lot of times in our daily life, that's the kind of statement we're using right here, an if-then conditional statement. So think about, in a shorter way of describing it, when at a given x value equals ax, right? Think about this is the way how I'm seeing it. If differentiable, right? That's one condition. If we have that condition, then it leads to, right? So the arrow right here, right? Or I don't even have to write the word if right here. So now just the arrow goes one way. So knowing differentiable, right? Knowing the function is differentiable, it leads to, it's a one-way thing right here. It leads to the function f of x, right? Is continuous. See what I'm saying now? So that's the conditional statement right here. We got a statement P, we know P, then we lead to having Q. Okay. Like, hey, if it rains, the ground is wet. Clear enough, right? The condition here is if it rains, right? Consequence, the ground is wet. So if we know that the function is differentiable, consequently the function will be continuous. Are you with me on that? But see, think about the rain and the wet ground here. If the ground is wet, does that necessarily mean that it's raining out there? No, because people can do sprinkler and all that, right? See what I'm saying now? So even if we have one conditional statement true, the opposite way, right? The opposite way saying that f, knowing that f being continuous does not imply back, right? Does not imply back that f of x is differentiable. See what I'm talking about? Okay. But I mean, there is that kind of form that we go in the opposite way. There is that form that we call it is the converse, right? In the logical, for people who study logic formally, they call that it's the converse of a conditional statement. So we're starting with a conditional statement is the way that we go reverse right there. That's called the converse. But for a conditional statement, the converse is not true. See what I'm saying now? The converse is not true. Okay? But here's the thing. Just back to what I was saying about the rain and wet ground right here. If it was raining, right? Or if it is raining, then the ground is going to be wet, right? So if the ground is not wet, can we imply that it's not raining? Sure, right? So in the way that it is right here, the ground, see, the ground is wet. If it's raining, right? If it's raining, lead to the ground is wet. What I was saying, if the ground is not wet, right? Yes, we can imply that it's not raining. See what I'm saying there? Okay. These two are equivalent again. Okay. And this is called the contrapositive. See what I'm saying now? So I brought up that example about the rain and the wet floor. You guys the wet ground. You guys okay with that, right? So how do we apply that into math right here? Think about it. So knowing the function is differentiable, yes, we can imply consequently that the function will be continuous, right? The converse, I made it clear, the converse was not true, right? Similar to the case of the rain and the wet ground again. But now you can say like this. If you know that the function is not continuous, f is, right, is not continuous. Okay? Isn't it true that we can lead to saying that the function f of x, right, is not differentiable? See that there? This is exactly the contrapositive statement of that beginning conditional statement again. So after you have passed some time writing it down, right there, that logic, and think through it, that connects perfectly into the picture we've seen earlier here. See, I was saying that, hey, graphically, if you spot in your graph, right, if you see a jump or like a hole that left out, a jump or a break, right, or a hole that left out like that, see, that implies not differentiable, right? We fail having a tangent line there. We fail placing a tangent line there, see? Because these are what the function is not continuous, or we're having this continuity. So yes, we will fail having a tangent line. We will fail being able to place a tangent line there. See what I mean? Okay. And so in the end, yes, that contrapositive statement was true for us. Okay. So that's the way how we're detecting it, and how it's connected consistently with the picture. Okay. All right, so, and the last thing I want to show, just before we wrapping up with differentiability, the last thing we want to look at is the definition. So, differentiability, being differentiable so far has been a property we learned only at one particular point, so we have to isolate ourselves to look at one specific point, right? And then, hey, having a tangent line there or not. But now there is a concept that being differentiable entirely, you see what I'm saying? No? So a function, right? A function f of x, right, is said to be, just simply we say that, hey, this function is differentiable, right? Function f of x is said to be differentiable if f of x is differentiable its domain. So this is the ultimate final definition that we're putting in, right? Because later on you will keep people, and even including me, referring to, hey, this function is a differentiable function, and that function is a differentiable function. The way I'm saying it is a very short term, a differentiable function. So what does that mean by a differentiable function? That means, think about it, if you see the graph, that graph right there, you can place a tangent line anywhere along that graph there. Okay? So famously, just think about famously any polynomial, right? Yes, any polynomial will be differentiable, meaning we can have a tangent line anywhere in the domain here. And then the rationals that we work with. So the rationals, yes, it's anywhere. Rational is also differentiable, except, right, just for short, right, in its domain. Right? It's the domain of the rational functions, any of those x values except the x that causing the denominator to equal 0. Right? So for short, as long as you stay in its domain, then any rational is also differentiable. Right? And then those sine of x, cosine of x, right? And those other ones are the trig functions, right? Yes. These guys are all differentiable in their domain. Yeah. And then we got the exponential, right? And then we got the logarithms. These are all differentiable, but this one once again in its domain.